On to our first example here. We want to find all absolute extrema of f of x on the interval -2, 1. So the first thing that we want to check is we want to find where the derivative is equal to 0. That's one of our potential locations for a critical number. So we'll go ahead and we'll do that. So f prime of x is equal to, and we're going to have to use the chain rule, right? Bring down the 2/3 2x cubed plus 16 to the -1/3. And then we have to use the chain rule. We have to multiply by the derivative of the inside. So times 6x squared. And we could simplify this a little bit. We could rewrite this as what? 6x squared times 2. That's 12x squared. And then this is all over 3 times 2x cubed plus 16 to the 1/3, which you could even simplify a little bit more. 12 over 3, that's 4. So I have 4x squared all over the cube root of 2x cubed plus 16. I'm going to scoot this over a little bit. Now, we would like to know when this thing's 0. Well, if you think back to maybe what you know about fractions, you know you need 0 over some non-zero number to end up with 0. Okay. Well, if we need 0 in the numerator, well, let's think about this. If we want f prime of x to equal 0, then that tells us that, again, that numerator must be 0. And if 4x squared is equal to 0, then x must equal 0. So this is one of our critical points. And one thing that we need to do with every single one of our critical points is plug them back into the original function. Because in the end, we're going to compare all these and see which y values are the largest, which ones are the smallest. Let's see, let's just put this right here. F of 0 is equal to, and then what we're going to have, 16 to the 2/3. So there's one of our options. Let's star it. All right, another option for where absolute extrema can occur. This is where our first derivative does not exist. Where it's undefined. Okay. So here is what we're really doing is just finding what values of x we can't plug into this. And I want you to note, you can take the cube root of positive and negative numbers, so that's not going to affect anything. The only issue we could run into here with our first derivative is if that denominator is 0. So let's go ahead and we'll set the denominator to 0. Well, if this is equal to 0, you know that what's in the cube root must be equal to 0. And if you, there we go, if you subtract by 16 on each side and then divide by 2, you get x cubed is equal to -8, which leaves us with x is equal to -2. And we'll go ahead and we'll also plug this into f. We want to see how large this is. Okay. And actually, we might not care. Let's see what our domain is here. And by domain, I mean the interval that we're trying to find our maximum and minimum. And so minus 2 is in that interval, so we do want to find it. Let's go up and see what f looked like. So 2x cubed, let's write that, 2x cubed, and I believe it was plus 16 to the 2/3. Yes. And 2 to the negative 3 is equal to minus 8, and then minus 8 times 2 is negative 8, or negative 8 times 2 is negative 16. So when we add up these two terms in the middle of these parentheses, we get 0. So 0 to the 2/3, which is just 0. All right, and we have one more location to check. So we've actually technically already checked this one here, because that's where the first derivative was undefined. And next, we want to check at 1. So f of 1 is equal to 2 times 1 cubed plus 16 to the 2/3. So this is just 18 to the 2/3. All right, and now is what we want to do is we want to compare all of these y values. See which one's the largest, which one's the smallest. Looks like here is our largest y value, and here is our smallest. F attains an absolute minimum at, and actually let's say of what? An absolute minimum of 0 at x equals negative 2, and f attains an absolute maximum of 18 to the 2/3 at x equals 1. And this is all over the interval minus 2 to 1. Okay. Is what I'd like us to do from here is just verify that what we found on paper matches what's happening in reality. And we're going to check that here on our TI-84 Plus. Okay. So I already have the original function typed in here, the 2x cubed plus 16 to the 2/3. Okay. Now let's adjust the windows. And let's do this so that it kind of matches the results we found. For one, we only care about x values going from minus 2 to 1. And why don't we just count by ones? Then in the y direction, we know the smallest value is 0, and we know that the largest one is 18 to the 2/3. And I need parentheses around that. 18 to the 2/3. And we can also just go ahead and count by ones here. That should be fine. And when we go to hit graph, we should see that the minimum occurs at one of the endpoints and the maximum occurs at the other. Okay. So let's go ahead and hit graph. Might have to adjust our windows. Let's see. Actually, this is looking pretty good. All right. So one of our maximums you can see is happening here at this right endpoint, and this is at x equals 1, and the y value is 18 to the 2/3, which matches our work. And the minimum you can see is at this end, and the minimum here is 0, and this is at x equals -2.